viscous liquid between two plates, either squeezing it together or pulling it apart. So if I put honey between two pieces of toast and stick them together and then try to pull them apart, I can't pull them apart immediately because of the viscosity of the honey, right? If I actually freeze the honey, then I'd never get those pieces of toast apart. And the thinner the joint, the stronger the joint, but that only goes as a square, whereas the viscosity can be changed by three processes by, let's say, something on the order of 10 orders of magnitude. And since 10 orders of magnitude works out to an increase in seconds, 10 to the 10 seconds is an increase of something on the order of, I can't remember, it was 30 years, something on a number of tens of years. We don't have to worry too much about adhesives that have solidified. So we have to figure out how to solidify adhesives. And your weekend assignment was to look around for some adhesive. I mean, I just told you one is, honey on a biscuit, or if you take a piece of biscuit and you put butter on it and you slap it together, well, the top slide will slide off on the molten butter, but if you put some honey in there, it'll stick together and then fall apart in your hands as you're eating it, right? So what adhesives did anybody notice this weekend? Anybody? Yeah. Egg? Yeah. Yep. And basically, what's that? Which of these three? Solvent removal, chemical reaction, or solidification? If it dries out, it's probably solvent removal. Okay, you're losing the water off of it. It hardens up. We're going to learn a little bit later that egg is basically just protein, and protein makes a wonderful adhesive. Proteins like to bond to surfaces, they can lower the surface energy of lots of things. And that's partly because proteins, well, they're complex enough molecules, they have both nonpolar and polar parts, and so they can either bond to nonpolar surfaces or to polar surfaces, depending on how they orient themselves. So proteins are great. In fact, we're going to learn about horses' hooves, right? You send the old horse to the glue factory, right? It turns out just about any protein will make a good adhesive. Okay, so egg. Now, egg when you cook it is not solvent. It's partially solvent removal, probably two-step process. Probably also a chemical reaction. I don't know enough about the chemistry of the protein and what's happening when you heat it up, but I bet there's a chemical reaction that's helping it harden up. Okay, as well. You're not boiling off all the water all at once, so there's probably a chemical reaction when you cook the egg. Anything else? Actually, the one I always wanted to do was to show you the difference of surface roughness. If you ever made some cheese toast and you put a piece of aluminum foil underneath, so you don't have to clean the cheese off the pan in the toaster oven. If you put nice smooth aluminum foil and the cheese leaks out on there, you can just peel it apart, right? Very carefully. If, on the other hand, it's old aluminum foil, it's got a bunch of wrinkles on it, you'll never get that cheese off, okay? You'll tear the aluminum foil apart. And I've always thought, well, to make some cheese on aluminum foil and bring it in and pass it around to the students. I think maybe one year I did that, but anyway, I don't think it went around all that well. But anyway, anything else? Any other adhesives anybody noticed? Yep. Okay. That's solidification. I mean, you're solidifying, I remember in second grade or third grade, this kid, got one of these pops out of carbon dioxide, and it was really cold. He stuck it on his tongue and got stuck, and he yanked it right off, and blood all over everywhere, He got scared. Anyway, good adhesive, right? Any other, what about a real adhesive? Yeah, go ahead. That's right, okay. So basically, if you add the solvent back to the wallpaper paste, you can do it that way. Good, okay. Yep. Yep. Okay, was this contact cement? Okay. I actually lost the heel on one of my shoes when I was traveling last week, and I came home, put some contact cement. Contact cement is basically a solvent removal, but it's also got something inside it called a tackifier. Okay, and Scotch tape is different than these things too, because it has tackiness, and we haven't talked about tackiness, but if I take some Scotch tape, you know that it's got tackiness to it. You can put it down. Tackiness is something that allows you to make a joint and then remove it. If you take Scotch tape and kind of keep on going back and forth like this, you know, eventually you can actually see early on, but later on, as you get the adhesive to kind of ball up and catch on certain things, you'll start seeing these little strands of rubber in between. And basically a tacky adhesive is it's actually an emulsion between a rubber, a bunch of little rubber bands, micro rubber bands, and the adhesive that wet each other. And essentially it gives it more peel strength because you've got these rubber bands kind of trying to pull it back even though you've separated it. The Stefan equation no longer works because I have these strings in between, okay, on something like that. Now it turns out Post-it notes. Post-it notes have a very interesting, sort of interesting adhesive. If you actually put Scotch tape on a piece of paper, I did. I just ripped that piece of paper and lost some paper onto the Scotch tape. Anybody know why you don't do that with the Post-it notes? You could say, well, they just use a less strong adhesive, but if you use a less strong adhesive, it's not going to stick very well. So it turns out Post-it notes actually have an array of little adhesive dots, which are basically just as strong as the Scotch tape. But what you're doing with Post-it notes is basically a perforated adhesive. And so it's easy to peel apart because you've basically got fracture mechanics working for you. You've got these cracks, if you will, or non-adhered regions in between. And if you're careful and you get the right type of dirt, okay, if you blow a little bit of fine dirt on the Post-it note adhesive, you actually can start to see the pattern. In some Post-it notes, you may have to go to a microscope or something, but basically Post-it notes have been printed with an array of little adhesive dots so that they have good kind of normal force tension, but they peel easily because there's a gap between each one of them. It's sort of like tearing the phone book in two. You're only breaking one little bond at a time, as opposed to one whole peeling apart one whole row of adhesive. What other adhesives have you got? Yep. Okay, wood glue on a table. And what's wood glue? What's solvent, reaction, or solidification? Solvent removal, it's water-based. Okay, same thing it's not all that different than the children's paste glue that they use in second grade. You ate it too. They made it peppermint flavored so you could eat it, right? It's water. That's water-based, and the wood glue is also water-based. Elmer's glue is basically a solvent base. Now, solvent base. Let's think about that a little bit. A postage stamp, at least the old postage stamps you had to lick, were just like your wallpaper. You're adding the solvent there. It comes as a solid adhesive, but then you liquefy it by putting some water or some saliva to it. You stick it on the paper, and in that case, it sticks fairly quickly because the water wicks away into the paper. If I stuck a postage stamp on a piece of glass, it's going to be hard for it to bond. It will take a lot longer for it to bond because the water's not going to evaporate away through the glass. And in fact, if I took that same adhesive and put it between two pieces of glass, it essentially would never bond. So solvent removal doesn't work between solid, non-porous adherents. Okay, so wood glue, if you read it, it said it doesn't work on metal. The reason it doesn't work on metal is not that it won't wet the metal, it's just that there's no way for the water to get out. Now you can bond a metal piece to a piece of wood, but now I only have one direction for the solvent to get out, and it'll take longer for it to solidify and set up, as far as that goes. It takes longer on hardwood than softwood. It just has to do with the porosity of what you've got. Okay, so you've covered on my little list. What about airplane glue? Solvent removal, that's what they breathe, right? You know, that's what they go to sniff, right? Is the volatile organics, right? To get a high. Yeah, model glue, yeah. Oh, you're right. I mean, it's solvent removal, but in that case, it actually dissolves part of the substrate. The solvent that's coming off dissolves the substrate and helps make it softer. In fact, if you put too much on, you know, and it's a small part starts to dissolve, right? It goes away, or you lose something. So you actually got several things going on there. You've got solvent removal because it does evaporate into the air, and that'll help it solidify. But you also are dissolving away part of the surface, trying to clean up that plastic surface. Why? Because those plastics have low surface energy to begin with. And so what you're doing is you're making a soft surface so that when you squeeze it together, you get rid of some of the surface roughness in between too. So you're forging it together, if you will. So there's a couple of things going on with actually bonding that type of plastic with a solvent-based glue. There are some glues, like if you take two pieces of plexiglass, polymethyl methacrylate, it turns out chloroform is the glue for plexiglass. You take two pieces of plexiglass, and if they have a nice machine surface, a nice tight surface, you put a drop of chloroform on there, and it will wick its way down. And there's really no glue. You're actually welding the plexiglass, if you will, by dissolving it and having it re-solidify. Now you can't make very thick joints because it is solvent removal, but chloroform has a fairly high vapor pressure. But if you have some chloroform, you just take an eyedropper and you just drop it on the joint, a tight joint between two pieces of plexiglass. The chloroform goes down, dissolves the plexiglass, and as the chloroform evaporates out, you end up with a weld, not just an adhesive joint, because you didn't bury contamination in that case. You dissolved it and re-solidified it. Okay. No, you mean the piping, like gas piping and stuff? Oh, yes. Okay, yes. For sprinkler systems and stuff, I'm pretty sure I haven't actually used that glue. But if you go and do PVC piping for plumbing, drainage piping and stuff, yeah, there is something in there. And although I think it actually has an emulsion, it's an emulsion and it leaves some solids behind. But I think it also, like airplane glue, dissolves part of the surface of the plastic. Yeah. Yeah, so okay, you're degreasing the surface with acetone. Okay. So that's basically a solvent removal too, because the acetone is going to evaporate away, right? I actually haven't used that. I've seen people use it, but I haven't studied it. So it's acetone cleaning. Again, plastic is hard to bond to because it has a low surface energy. It's got van der Waals bonds. And so there's only so many things that want to displace the plastic and contaminate a plastic surface, because plastics have some of the lowest surface energies, like 40 ergs per square centimeter, which is 0.04 joules per square meter. What happens? What? Yeah. Yeah. So actually, in that case, you've got multiple things going on in some of these things. It's not just one. It can be a combination of these things, and you actually have a variation on welding in some of these plastics. It's not just straight adhesive bonding. Okay, so we've done a lot of solvent removal. We haven't hit very many. We've only hit a couple of chemical reaction ones. Yeah. Oh yeah, hot melt glues, right? Glue gun, you heat it up, just temperature based. Asphalt, you heat up the asphalt is hot when you bring it from the asphalt plant. What is asphalt? It's just heavy hydrocarbons. They're not quite, they haven't solidified all the way to coal, but they're solid at tar is solid at room temperature. You heat it up, and you melt it, and you mix it with a bunch of aggregate, stone and gravel, and old broken up bottles or whatever it is you're going to put in there. I mean, that's one of the things. Everybody who's got a solid waste disposal problem says, oh, we'll just mix it in with asphalt and pave the roads with it. The problem is we don't have enough roads for all the solid waste we have. But basically, asphalt is a hot melt adhesive. You're solidifying the asphalt. They put it down hot, and as it solidifies, it toughens up. And actually, it does toughen. If it gets really cold, it actually gets brittle, and that's a problem. But you actually want the asphalt to give a little bit. You want a little bit of flexion, right? So that it will, when the heavy loads go over it, it bends rather than breaks. Okay. So asphalt's a good solidifier. Hot melt glue guns are basically just proteins and whatnot that have been melted. Chemical reaction, epoxies, right? And epoxy is you mix A and B, and you get a chemical reaction. And basically, you take one polymer and another polymer, and the catalyst, the B component, the A component is the two polymers. The catalyst actually changes the bond and links those two polymers into a bigger polymer. And heavier polymers have higher melting temperature, so by chemical reaction, I essentially raise the melting temperature by making big polymers out of little polymers. But there's some others. What about Krazy Glue? Anybody? Okay. Actually, super glue appears to be strong for a couple reasons. One is that super glue is what's known as a cyanoacrylate. Okay, so it has a CN bond, okay? And let's see if I may have, from years past, left let's see. No, okay. I guess I didn't mark cyanoacrylates, although I guess I could look it up in the front. First of all, the cyanoacrylates are pretty pricey. Okay, 34, page 569. Because they're very special polymers. And I think this is the book. Okay. The unique adhesive activity of the alkyl 2 cyanoacrylates was discovered more than 20 years ago. Well, this book's about 1970s. So anyway. During basic research directed toward characterizing polymers derived from 1,1 disubstituted ethylenes. If you're an organic chemist, maybe you know what that means. I don't. During a routine measurement of the refractive index of a freshly prepared sample, the prisms of the refractometer were adhered. Okay, so they glued their glass together. Within a few hours, the full implication of these inseparable prisms was apparent as scientists used the cyanoacrylate to form strong bonds between a variety of substrates. This marked the beginning of the development of these adhesives. Okay, they have the ability to polymerize rapidly at room temperature. They're very low viscosity. I mean, they're like water, right? When you drop it on there, which means they get down into the pores. Some of the other adhesives are kind of thick, and they don't get down into the mechanical interlocking pores as well. So the cyanoacrylates take care of the surface roughness problem very well, and then they solidify. And so it's really because they do a very good job of mechanical interlocking. They appear to be extra strong. They also are strong. We think of them as strong because we glue our fingers together, right? Or if you wipe your nose or something, you know, or your lips, you know, can't talk, because they polymerize very rapidly. That's partly because they have low viscosity to begin with, and so the molecules can diffuse around and find the polymer chains early on. But it turns out you didn't add a B polymer, right? A B component to it. Anybody know what the B component is? Water. It's basically hydroxyl ion, which is in water. And so cyanoacrylates, it'll tell you they don't work as well on wood. They work on wood, but they're a little slower because wood is usually acidic. If you want to use Krazy Glue on wood, take some Drano and paint the surface with Drano first, because Drano is basically a basic solution. It's sodium hydroxide. So if you paint the surface and make the surface a high pH rather than a low pH, the cyanoacrylate will have more hydroxyl ions, and it's the hydroxyl ion that does the polymerization. Okay, but the main reason they seem to be stronger is because they have very low viscosity. They give you good mechanical interlocking. Okay, but they solidify to a similar type of viscosity as anything else. They actually have a viscosity similar to any other plastic, like polystyrene or polymethyl methacrylate and things like that. Okay, so it's mostly just because they're a very fluid thing, and so they get down into the pores. Now your skin is slightly basic, unless you've been playing around with Coca-Cola or something. Your skin is slightly basic, and that's why it glues your fingers together so well. Okay, there's plenty of hydroxyl ion there. Okay. You don't have to paint your hand with Drano to bond your fingers together. Let's see. We talked about epoxies. Anaerobics, like Loctite. Loctite, I mean, it's a billion-dollar corporation now, but they basically learned that there were certain types of polymers that would polymerize with the lack of oxygen. So if you go look carefully at a bottle of Loctite, anybody know what Loctite is? Anybody not know? Loctite is basically a fairly fluid adhesive that if I put a bolt in a hole and I don't have a lock washer, I can put a drop of Loctite and it'll go down in there between the threads and it'll solidify inside there. And I didn't add a B component. It turns out what I did is I subtracted a B component. It's the oxygen in the air that keeps that polymer from polymerizing. That's why it's called an anaerobic, without oxygen. Okay? Remember, aerobics is doing a lot of exercise to get a lot of oxygen into the heart. You know, suffocation is anaerobic. You're taking the oxygen away. Well, Loctite is an anaerobic polymerizer. And so these polymers in the absence of oxygen. If you look very carefully at a bottle of Loctite, somewhere around the cap or the side, they've introduced a little hole. Small enough in some way so the stuff doesn't leak out. But they have to have oxygen in there, otherwise, if you take the cap off, the whole thing would have been solidified, right? So you can't. It's not always easy to find where they put it. I've looked a couple times. I've usually been able to find where the hole is in the little tube of Loctite or whatever. But there's a hole in the container to allow air to get in. Okay. Otherwise, it'll just harden up on you. So anaerobics, epoxies, hot melts. Anybody have any other adhesive they're curious about? Okay, there are other adhesives. In fact, if you go to the Handbook of Adhesives, this is second edition. There is a third edition, but I actually like the second edition better. The actual date on this is 1977. So, anyway, the reason I like the second edition is because it's got an article which I handed out to you by what's his name? It's the third chapter, I think. Yeah. Who's the guy? It's chapter 3. It's by Zisman, W.A. Zisman. It says influence of constitution on adhesion. And a lot of what we're talking about, I basically just stole from this chapter 3 in here. Zisman was a researcher at the Naval Research Laboratory, specialist on adhesives. He's retired now. Actually, he may have passed away by now. But in any case, they don't have his chapter in the third edition, and I think it's one of the better things I've seen on surface energy and adhesion. However, if you want to know, most of this book basically is section B. The first 5 chapters are fundamentals, and the next 35 chapters are adhesive materials. Animal glues, we talked about horses' hooves, okay, but it really doesn't matter too much. There is casein glues. Casein basically is the leftover when you make cheese from milk. So you take the protein from the milk, and after you got the curds in the whey, W-H-E-Y, right? No whey, no, not the whey. Whey, okay. In this case, the whey has casein, which is a protein, and it makes a glue. So you can sell the curds for cottage cheese, or you can make real cheese out of it, but you can sell some of the whey for a casing glue. Anybody know what gurry is? G-U-R-R-Y? You got to have a pretty good dictionary to find it. But it used to be a major product of Massachusetts. G-U-R-R-Y. Didn't have to be careful. Gurry is old fish heads and fish bones. After you fillet the fish, you end up with the leftover. And maybe cats would like it, but they choke on the bones or whatever. So there's only so much you can do with gurry, and they used to just take it out to the harbor and dump it. And then environmentalists complained, so they took it further out and dumped it. Well, there's always a solution, right? But you actually, fish glues or fish proteins can make glues too. And gurry is basically fish protein, and so it turns out the chapter 8 here is fish glue. Now, it is an important product of Massachusetts, and back in the old days when I'd pay my taxes in Massachusetts, I was stupid enough to actually lick the envelope. I don't do that anymore because it tastes terrible. And I'm convinced that because they're using a natural Massachusetts product. They're probably using fish glue for the, so you have, I call it adding insult to injury. First you have to pay the taxes, then you have to taste the fish glue as you gives a new meaning to leaving a bad taste in your mouth. Soybean glues, blood glues, okay? Blood has got protein in it. You can make glue out of it. Starch-based adhesives. So you can use old corn stalks if you want. Cellulosics, basically any type of organic or polymer or protein. Then they get into rubber-based adhesives. Those are the ones that have tackiness to them. Polysulfides, amino acid resins, epoxies, polyurethanes. Now, one of the silicone adhesives, okay, so there's all kinds of different adhesives. The cheapest ones, obviously, if you're using whey or corn stalks or blood from a slaughterhouse, then these things are fairly inexpensive. You're talking something on the order of 10 cents a pound for old fish heads that have been processed. They took the bones out, right? And they also put some other things in there to deodorize it and things like that. They don't take the taste out, though. So those are 10 cents a pound. And I could use some of those. The problem is most of those are water-based. So if I'm making indoor plywood, I can use a nice, cheap, starch-based adhesive or something. And the reason it's indoors is because if it gets wet, just like your wallpaper, the solvent's added back and the whole thing peels apart. Now, if I want a higher grade of plywood, an outdoor grade of plywood, I'm going to use an adhesive that's got to be pretty cheap. But it might be 20 cents a pound because now I've got to use some sort of oil-based thing that I could have burned it, right, or something instead of making it into a glue. But now when it rains, it doesn't. The solvent isn't added back when it rains. I may have had a solvent in it. That solvent diffused away into the wood, the porous wood, to make the plywood. So I can have 10 cent a pound adhesives. I can get to the cyanoacrylates, which may be on the order of $100 a pound because you've actually got to go through a chemical reaction vessel and you've got to make a compound that's not, that's got to be synthesized by a chemical engineer in a big plant. And there are others, like some of the polyimides and stuff, that have very high temperature capability. By very high temperature for a polymer person, what are we talking about? Anybody have any idea? 400 degrees, yeah. Fahrenheit or F? Fahrenheit or C? Yeah, either one. I mean, we're pretty loose here on things. We don't care whether it's C or Fahrenheit. Turns out some of the silicones can go to 400 C. Some of the cheaper ones will only go to, the polyimides will only go to 400 F, but some of them will get to 350 C. So, and the silicones actually, the silicon-oxygen bond being stronger than a carbon-carbon bond, some of the silicones, if you get a little cross-linking in some of those things, silicone rubber you can put in up to 400 C or something like that. So 400 is a good number, whether it's C or F. Okay, good answer. So some of these polyimides can cost $400 a pound. It turns out when they first had problems in the automotive industry with rusting through of car, actually they didn't have problems. What happened was we had the oil crisis in 73 and then 78. And it used to be people didn't really mind buying a new car every 5 years. But they started getting more electronics and better engines and stuff. And so people wanted cars to last 7 years and then 10 years. And now I think most people kind of hope that whether they keep the car forever or not, they hope that it'll last for 10 years, so it'll have some resale value after 5. And some of you, in your current economic state of affairs, hope to last for 15 because you bought it when it was 11 years old, right? But in any case, cars were basically just straight steel sheet in the early 1970s. And after the 73 oil crisis, they decided they wanted to improve the rust-through performance of the sheet metal. So they started galvanizing it, putting a zinc coating on. And they tried to weld it, resistive spot weld it, and you actually should. Did they see the movie, Chris, of the resistive spot welding? So you saw that was, you could see the zinc melting on the surface and globs of zinc coming out and stuff in those high-speed movies. There were lots of problems, and we can talk about it later about galvanized steel. But typically today, for one of the big three former U.S. companies, Chrysler's no longer a U.S. company, but everything except the roof is galvanized. You go to a Japanese car, and certainly everything on the bottom is galvanized, not everything along the side, and certainly not the roof. But basically, where you're going to get rock salt and other things in New England, you've got to worry about rust through. Now, you go to California or Arizona, and you see cars that are 40 years old on the highways all the time, because they don't rust out, because you don't put salt on the roads in the winter. At least it's kind of silly to put salt on the roads, except in Death Valley. I guess it's already there. In any case, they wanted to extend the life, and they started giving 5-year rust-through warranties, and now 7 years, I think, is the typical rust-through warranty. And so that created problems for welding of it, and so they started trying to adhesively bond it. And so you don't want a car from the early 1980s that was adhesively bonded. One of the worst places is in the doors. The doors, if you try to make a spot weld, people are going to see the edge where the door is. You got an outer panel and an inner panel. If you come in these two big copper electrodes and weld it, you're going to end up with a spot. Now, if you want to lift up the hood of your car and you want to look at how they join the sheet metal, you'll see the spot welds. They're painted over, but you'll see the indentations. Well, who cares under the hood? I mean, you don't even notice it. You're looking at the engine, right? But you certainly don't want to see that on the door. And so they call it the hem flange. Basically, they just take the sheet metal and fold it over on itself. And then they used to try to spot weld those, and in steel, bare steel, they could without leaving indentations. But then in the early 80s, they started going to galvanized, and they were leaving bad marks, and that was creating all kinds of problems. So then they just started adhesively bonding them. And of course, the big thing in Detroit is cost, and so they used the 50 cent to $1 a pound adhesives. And these worked good for the first 2 or 3 years, okay? And after 4 or 5 years, if you take one of those doors and hit it with a tack hammer, it'll fall apart because the adhesive basically is completely debonded. The adhesive doesn't have long-term strength. The cheap ones are water-based. And guess what? It rains out there, okay? Even in Arizona, sometimes it rains. So, I've seen doors just completely fall apart with almost no deformation. They just pull. You can pull them apart because there's no adhesive left. The adhesive is debonded from the surface. Nowadays, it's okay. From like about 1990 on, the automotive companies realized this was a problem structurally, and people didn't like their doors falling apart after 3 or 4 years. Although it was out of warranty, so it was really okay. But even so, they now use adhesives that are about $10 or $12 a pound. But you gotta remember, in the automotive industry, that's pretty pricey because the overall structure. Anybody remember what the value of a pound saved in a automobile is over the life of the vehicle? $2 a pound. So the basic structure can't cost more than $2 a pound on average, and using $12 a pound adhesive means I got to use something cheaper somewhere else, right? Well, it turns out steel's a little cheaper, but you're pushing the limits when you're going to $12 a pound adhesive for automobiles. Now, on the other hand, Boeing, when they do lots of adhesive bonding, for reasons we'll talk about in just a second, they don't mind spending, well, they don't like spending $400 a pound for an adhesive, but their product is worth $200 a pound on average over the life of the vehicle, the main structure, and so they can afford to spend $400 or $100 a pound is quite acceptable in terms of the value and the weight savings you can get. And the reason you can get some weight savings, particularly in an aircraft which has to go about 100,000 hours, the car goes 100,000 miles, which hopefully is less than 100,000 hours, okay? Which reminds me that, but an aircraft, commercial aircraft, does 100,000 hours. Although there's actually a joke about Texas on that, and that's this guy comes from the old country, and he comes to Texas, and he's very, very successful. He buys himself a big ranch, and very pleased with his ranch, and he goes back to the old country a few years later, and he's going to tell all the people there in the village square how successful he's been. And he's telling them about his ranch in Texas, and he's telling them how he can drive, he can get in his car and he can drive for 10 minutes north or 10 minutes south or 10 minutes east or 10 minutes west, and he's still on his property. Texas is so big and his ranch is so big, and everybody in town, village square, is just kind of sitting there, you know, whittling or whatever they're doing. They're not paying too much attention. And he says, well, do you understand? And this old man says, no, I understand completely. I had a car like that once. So, anyway, if I take two sheets of material and I want to adhesively bond them, it turns out if I take unit depth into the board and I pull on these things in tension, okay, yeah, that's not a very good arrow. Neither one of them are very good arrows. So I'm pulling on it in tension. This has some yield strength times the thickness T times unit depth into the board. And this is going to have some overlap distance, L, and it will have, the adhesive will have some shear strength of the adhesive times the area, which is L times 1 if it's unit depth into the board. And so it turns out you can look at this, that sigma y times T, if I want to know when the strength of the base material is equal to the overlap joint, it's just tau of the adhesive times L, or sigma y of the base material divided by the shear strength of the adhesive is going to be equal to L over T. So I've got an aspect ratio here of L over T. What's the overlap distance to the thickness, T? And in fact, in worrying about that, the thicker the base material, the greater the overlap distance for a given adhesive, and that sort of makes sense, okay? The greater the strength of the base material, the strength of the adhesive, the greater the overlap distance that I'm going to need in order to match the strength of these two. If I have a shorter overlap distance, it's definitely going to fail in the adhesive. If I have a bigger overlap distance, then hopefully it fails in the base material, and I can't expect anything any better than that. Now, one of the problems here is if this overlap distance gets very great, then I've lost a significant advantage because I'm doubling up the material here. That costs money, it costs weight, does lots of things. But one significant advantage of this is that I get a very, because the adhesive tends to yield at a lower strength, I get a good distribution of the stresses in here. And so an adhesively bonded joint is generally very good in a fatigue-loaded situation. And that's exactly what you've got in aircraft. So Boeing will use expensive adhesives that have very good moisture resistance, will last for 20 or 30 years, but they're going to pay between $100 and $400 a pound for those types of adhesives. They're also going to do things like anodize the surface of that aluminum to improve the bond strength, so far as that goes, so they don't have to have as much overlap distance. It turns out, until recent years, they usually would also put rivets in these joints too. And one guy told me the story. He was walking through and giving a tour of Boeing, and they were talking about how wonderful their bonding technology was, and they could make the whole airplane with adhesives. And they went out and he saw them riveted. He saw them putting adhesives on and then riveting through the adhesive. And he says, well, why are you doing that? I said, oh, just to make sure, okay? Because they needed to get a little more experience. It takes a while to get 30 years worth of experience on adhesive joints. Okay. And in fact, it does take 30 years. It's hard to run an accelerated aging test. In fact, the National Research Council just finished a report, I think they finished it last year, for the Air Force on evaluating the strength of adhesive joints in aging aircraft. Because, you know, when they built the aircraft, they had a 25-year life, and they're now 40 years old. If it's a B-52, some of those things are 45 years old now. And the adhesives were not as good in 1955. And so, you know, you're kind of wondering, you know, why you have more rattles in it than you used to. In any case. Any questions on these adhesives? Now, in order to get wetting of the adhesive, or getting mechanical interlocking of the adhesive has to have a low surface energy. So if I think of some groove in the surface, and I get wetting, the liquid will find its way down in here and eventually fill it up, and when it solidifies, I end up with a good strong bond, and that's why cyanoacrylates or Krazy Glue, they get down in those pores better than anything else because they have a nice low viscosity. With low viscosity, they can get right down into the sharpest corners, and they can turn corners in these complex phosphated or chromated surfaces that have very rough surfaces. Not everything's a nice little V shape. However, one material, Teflon, and early on, I think first day of class or whenever, someone said, you know, how do you bond Teflon to the pot? And we talked about Millennium cookware, where you essentially infiltrate it under pressure, the Teflon into this porous surface on the pot. There's another way, which I've actually never used, to try to get mechanical interlocking on Teflon. The main problem with Teflon, let's say I just put water on the surface, is Teflon has such a low surface energy that the liquid's got to come in this way, and it's going to have a contact angle if it's that's going to be kind of non-wetting, and it'll never really get down in there. You can't get it down into the bottom of the pores. So you always end up with a poor joint because I've just got a little bit of mechanical adhesion in here, and I don't get down into the deep pores. Now I can't remember if I read this once or I figured this out for myself. So who knows? It may be patentable. How do you get the adhesive? Let's say it's water. I guess maybe I did read this once. How do you get, ordinarily, if you try to put water on Teflon, let's say you sprinkle some water on Teflon, a sheet of Teflon, and put it in the freezer so you have little drops of ice. You can then kind of flick those drops of ice off because the water didn't get down into the pores because water has a high contact angle with the Teflon. Teflon's got one of the lowest surface energies, about 20 ergs per square centimeter. You know, metals are 1,000 ergs per square centimeter. Ceramics are 400. Most polymers are 70 or 80. But Teflon, because of this fluorine-carbon bond, which is fairly stable, has the lowest surface energies of any material, well, not Teflon itself, but the fluorinated hydrocarbons. If you go to Zisman, he shows different fluorinated hydrocarbons, and some of them get down as low as 17 ergs per square centimeter. How can I get, anybody have an idea, how to get the water down in here on the Teflon? Well, if you actually go through something like this, remember the delta P is gamma times the curvature. Okay, and curvature is 1 over R1 plus 1 over R2. Well, if R gets to be very small, the curvature, the pressure that you're going to have is going to be huge. So yes, you can apply pressure, but you're probably going to deform your Teflon before you really get it down in small pores. Yep, Chris? Yeah, but you took this class before, didn't you? Okay. If you think of trying to put a liquid on top of a solid, you can't solve this problem. Okay. However, if I think of putting a vapor on this and having a temperature gradient so that I've got a hot steam up here and this thing's being cooled, I will vapor deposit the water in here down from the bottom, and as it condenses down in here, its wetting angle is still non-wetting, but now it's non-wetting in the proper direction. You know, I keep on condensing water until I get water across the surface. I could make a very strong bond that it now has to solidify. So if I had some surface that I had to bond, and I'm willing to pay the price of vapor depositing an adhesive, even though it's non-wetting, okay, I could make a mechanical interlock bond. Yep. Well, we'll turn into a ball up here, okay? Oh, balling on the bottom because it's down inside here. I mean, the lowest, it has to nucleate somehow here, right? Now, it's possible if you don't have, if things are really bad, if you don't, this has to be a pretty low surface energy material too. And if there's not a big difference, then if you had a huge angle here, then yes, the thing could ball up. If it's a 180-degree contact angle, it still won't work. But you can get adhesives with 30 or 40 ergs per square centimeter. And if you had a surface like Teflon at 20, you could, and I've read that you can do this. Actually, water has 70 or 80 ergs per square centimeter, and supposedly you can do this with water on Teflon. I've never tried it, but I did read it somewhere about water with Teflon, on Teflon, getting it to stick. Okay? So I guess that's enough for today on adhesive bonding.